In this video, I'll be explaining the concept on PDA. PDA is nothing but push down automata. Specifically, I'm going to talk about non-deterministic PDA. Let us see the definition. A push down automata or PDA is a finite state machine that has been augmented by a single stack. So in case of push down automata, we have a support of single stack. That is why we'll be able to express the context-free grammar efficiently, whereas the context-free grammar was not able to represent in case of finite state machine. That's why we have here a machine called a push down automata. Let's see the definition now. Push down automata M is a 6-tuple representation k, sigma, tau, delta, and s, a. K is the finite set of states, sigma is the input alphabet, tau is the stack alphabet, s belongs to k is the start state, a subset k is the set of accepting states, and delta is the transition relation. It is a finite subset of these, that is current state, input can be as per your grammar, as per the language. Then also here we are going to include epsilon because it is a non-deterministic PDA. Then we have tau star. Tau star always represents the stack variable, stack contents, that is alphabets that are used in the stack. Next, and which will give you another state, that is next state, and the stack symbols. So these are the change that is going to happen based on the transitions. Next we'll see the configuration of a PDA. Configuration of a PDA is an element of k cross sigma star cross tau star. So this is represented using this is nothing but a configuration. When it comes to configuration, it is like we can tell the particular state of a PDA, and this configuration always captures three things that can make a difference to M's future behavior. That can make difference to M's future behavior. It's current state, the input that is still left to read, and the contents of stack. So these three things can be get affected. Okay. Now we will use the following notational convention for describes n stack as a string. Let's try to understand the stack of a PDA now. The top of the stack is to the left of the string. That is stack topmost symbol will be in the left of the string. That is, here if I consider CAB, it is whereas the character C is on the topmost string. So you have to read this character from top to bottom. Okay, so this character will be the leftmost character. Now, for example, if we have in your case, that is in the string in the stack, for example, if you have there are a sequence of C1 to C1 to C2 to Cn of characters is pushed onto the stack. So C1, C2, C3 and Cn characters are pushed onto the stack. They will be pushed rightmost first. So if the value of the stack before the push was yes, suppose there was yes character in the stack, then this will be read as C1. As I told, topmost will be, you have to read from top to bottom, isn't it? First this will be popped, that's why always the topmost character will be popped out. So that will go to the leftmost, that will become the first character of the string. That is first in the sense in that particular time that will be the leftmost character. So next C2, next C3 and so on up till Cn, then yes. Okay, this is what the characters are. This is how the stack is represented. Next we'll see the examples related to PDA. Before moving further, Let's understand the important concept related to the examples, that is transitions. We can draw a transition like this, that is q1 c gamma 1 comma q2 comma gamma 2. What is the meaning of this? So I have already told transition relation is represented as k, the state, cross sigma star, because union also included, and then tau star which will map to k cross tau star. You can see here, this is what the present state and this will be the next state. So this is the effect q2 comma y2 is gamma 2 is the effect of q1 c gamma 1. Let me explain this. This is k, that is the state, and this is sigma star, that is the from the alphabet or epsilon. So c is the character either from the alphabet or epsilon. Then gamma 1 is the stack top symbols, and then q2 comma y2 gamma 2 q2 is the state, and this will be again stack symbol. So that is and this will be also represented as, there is in the figure, you have to draw a arc from q1 to q2 and that need to be labeled as, you can see here, c bar gamma 1 bar gamma 2. Okay, there will be a arc from q1 to q2 and which will be labeled as c gamma 1 and gamma 2. That is this way. This is how you need to be labeled. And what is the meaning of this label? So if a c matches any input, then gamma 1 matches the top of the stack. If gamma 1 matches the top of the stack, and the transition from q1 q2 can be taken, in which case c should be removed from the input. If suppose gamma 1 matches the top of the stack and there is and you can show the transition from, there is a transition from q1 to q2 can be taken, in which case c should be removed from the input and gamma 1 should be popped from the stack. Gamma 1 should be popped and gamma 2 need to be pushed onto the stack. That's the representation. So always remember, these are the three characters represents: input character, /pop character, and then bar push character. If this c character is epsilon, if you get a c character as epsilon, then the transition can be taken without consuming any input. That means you can have a transition from q1 to q2, but there is no character read from the input. So this, see, you can see in case of, if there is a character c, then what you have to that particular character should be removed from the input. Okay, whereas in this case that is not going to happen. In case if it is c is epsilon, if you get something like this, gamma 1 or gamma 2, what happens? You can take a transition from q1 to q2, but no character will be read from the input. Okay, no character will be read from the input. Suppose next case, if gamma 1 is epsilon and you have read up, if there is a match in the c character, then what you have to do? And there is a gamma 2. Okay, in that case what you can do is, the transition can be taken from q1 to q2. Transition can be taken from q1 to q2, q1, and then there is q2, and it is written as labeled as c gamma comma gamma 2. Now upon reading c character, you can take a transition from q1 to q2. You can move here, but you since the second character represents the pop character, you're not here. You can check it, transition can be taken without checking the stack or popping anything, without checking the stack or popping anything. So here you're not going to pop anything, but you can push it. Okay, you can push. Next, when it is gamma 2 is epsilon, for example, if we have something like this, see, this is gamma 1 and this is gamma 2. Gamma 2 is epsilon. In this case, nothing is pushed onto the stack. You can see here, nothing is pushed onto the stack when the transition is taken. As we did with FSMs, we will use the double circle to indicate the accepting state. Okay. Whereas when in this case, C gamma 1 comma epsilon, we are not going to pop anything. We are not going to push anything. Whereas in this case, we are not consuming any input. Here we are not popping anything if this is the case. And whereas in this case, we are not pushing anything onto the stack. Okay. And like as usual, like FSMs, here also we will represent accepting state as a double circle. Okay. Now we'll see the example. Now here we'll construct a PDA for balanced parenthesis language. For that we were not able to draw a FSM because of the reason was that there was a we were not able to compare the number of opening parentheses with the closing parentheses in case of FSM. But here we have option of a stack and which will hold those is opening a parenthesis. Okay, so who will remember the opening parenthesis? In this case PDA stack will hold the opening parenthesis, and that will remember the opening parenthesis for us to compare with the closing parenthesis. Okay, this 6 tuples you can represent it later. First let me explain how did I got this. So first of all, as usual, start with the start state. Start with the start state, and start state is yes. Start state is yes. I'm going to name it as yes. Now, what I have to do, as I told, because it is a parenthesis are balanced. So if there are 2 opening parentheses, we need to have 2 closing parentheses. It may be in this format or this format. Okay. Let me consider this example. Okay, the first example, so that it will be easier to understand. Whenever I get opening parenthesis, what I will do is I will push it onto the stack. Push it onto the stack. Okay, whenever I get closing parenthesis, I will pop the one parenthesis. For this one closing parenthesis, I will remove one opening parenthesis from the stack. Similarly, for the another one, I will remove other one. Okay. When you come to know that your input is over and the stack is empty, then you can say that, and you are in the accepting state, for these reasons, these 3 reasons, you can tell that particular input has been accepted. So now here, what did I say? Whenever you get opening parenthesis, you should do what? So I will make use of the same state. Whenever I get opening parenthesis, I will just push it onto the stack. You can see here, I will just push the character opening parenthesis onto the stack. I am not going to pop anything. But whenever I get closing parenthesis, I will do what? I will pop what? As I said, whenever I get closing parenthesis, I will pop the opening parenthesis. So that is the second character. So again, let me remind you, first character is the input character you are going to read. Second one is the popping character. Third one is the pushing character. Now I want to pop opening parenthesis. That's why. And then I'm not going to push anything onto the stack. So Once, since everything is done at this portion, so this can be at this state, this can be double circled. So this is about the balanced parenthesis PDA. Now we have to represent the 6 tuple k sigma tau delta s comma a. K is the set of states. How many states we have? Only one. Yes. Sigma is opening parenthesis and closing parenthesis. Tau is the stack character. You can see here in the stack I have stored only opening parenthesis, that I have represented here. Then the start state, accepting state is the start state itself. So that's why yes. Then we have to represent the transition function. How to represent the transition function? There are only two transitions here. You can see here, that is one on this and one on this. So here yes on yes goes where? That is, you can write yes to yes itself, it goes, isn't it? So that can be represented. This is for the first one I am writing here. It goes to yes to yes itself. And reading which character? So first two characters you write here, open parenthesis and close, and the last character you can write it here. Okay. Next, similarly another transition we have representing this. So how do I write that? That also to yes to yes. Okay, comma. Here also two brackets, comma. This should be within the one parenthesis. So yes to yes, and here these two are the first two characters I am going to write here, closing and opening, and here epsilon. So you can see here, that is how we have represented. This is for the first transition and this is for the another transition. This is for, so again let me tell you, this is for this, okay, and this one is for this one. So that's about the PDA of balanced parenthesis language. Now we'll see the computation on input string, double parenthesis, double open parenthesis, followed by double closing parenthesis, and then one parenthesis and closing parenthesis. On this input, I am going to perform the computation for the PDA which just we have constructed. So this is that PDA. Now we'll see actually this input string is according to this PDA or not. Now for that we need to have three fields. One is the start symbol. We have to start the computation from the start symbol, and then this portion will be input string, this portion will be input string, and then finally the stack contents. So initially stack content is empty. Okay, so first field represents the state, current state. So initially for the first time current state has to be the start state, then the input string, and finally the stack character. So initially the stack content is empty. So when finally at the end, to tell this input string is accepted, so you need to have a final state. So this state need to be a final state, and the input characters need to be empty, and then this field, that is input field, need to be empty, and then that means you must have processed those characters, and after that stack content also must be empty. When you come to this situation, you can tell that input string is accepted. Okay, let me start here. As I told, start state, and then the input string, start state, and then the input string which is supposed to process, and it is here empty. And later in the next step, it is this tells the step from this separates the step one step from the other. So next will be what? So you will be reading the first character of the input. You will be reading the first character of the input. First character is this. So when you read this first character, what you will do? and you know that PDA makes use of the stack. So whenever you find open parenthesis, that will be pushed onto the stack. So you can see now in the next step here that first opening parenthesis is gone. What is remaining? So once this is moved, first character is moved, that will be pushed onto the stack. Okay, that is moved in the sense it is pushed onto the stack. So what is remaining in the input character? This only these many characters. That is what's shown here. Then opening parenthesis will be in the stack. So that is this particular field represents the stack content. Next, after finishing this step, next we will move on to the next step. And remember, whenever you read S on opening parenthesis, it goes to the same state. That is why this S. Okay, that is why this is. And don't think that every time it need to be yes. So it says that when S reads the open character, that is open parenthesis, it will go to which state? It goes to the same state. That's why this is. Now next character to be read is S on opening parenthesis. S on opening parenthesis, this is the input character, right? This is the input. S on open parenthesis goes to S itself. So that's why S, and then S on opening parenthesis does what job? It just pushes this character onto the stack. So third field says push which character onto the stack, and whereas this says what need to be popped. Okay, so now again I will push opening parenthesis onto the stack. After that close parenthesis. So here what is remaining? This, if you push this onto the stack, so here you can see what is remaining. It is remaining only these, and here in the stack there are two opening brackets. Next comes to S on closing parenthesis. S on closing parenthesis is this. S on closing parenthesis goes to S itself. So let's write S. Yes, I have written. After that, what does it do? Whenever S on closing parenthesis pops one opening parenthesis from the stack. So you can see that one character is popped. So that's why when you read this character, what is remaining in the input? So only these many. So that is what written here, and one opening parenthesis, that is topmost one, is popped. So topmost one is popped. So that is popped. So what is remaining? This one. Okay. Next, when S on closing parenthesis does what? Goes to the same state again. Next, what is remaining here? After reading this character, what is remaining? Only these. That will be written here. And S on closing parenthesis, what does it do? Pops the opening bracket from the opening parenthesis from the stack. So that's why stack is now empty. Nothing is there in the stack. Okay. Then again, S on opening parenthesis goes to S state itself. Next, that is, it also tells S on opening parenthesis goes to S state and pushes this character opening parenthesis onto the stack. Now again, stack will have now opening parenthesis, and when it reads the closing parenthesis here, what it will do? It goes to S state, but opening parenthesis will be popped from the stack. You can see here, when it reads what is remaining, the stack content is this. When it reads the closing parenthesis, it goes to S state, fine, but the contents of the stack will be popped. So that's why this place also will be empty, and after processing this character, even input character also becomes empty. So this is how we have to do the computation on input. Next we'll see another input. Example of rejecting input string. So that's why I will consider here this example. Looking at this, one thing is clear: the number of opening bracket and number of closing parentheses is unequal. So clearly, now let's see the string. So again, I start from the yes start state. Start state here is yes, and then I will write the input character, and then initially stack contents are empty. Now when you read the first character, that is opening bracket, what happens? Yes on opening bracket goes to yes state itself. That's why next also yes state. Yes on opening bracket goes to yes state itself, but pushes that character onto the stack. So this opening bracket will be into the stack. So what is remaining in the stack? In the stack, after processing this, there has to be here one more opening bracket. Okay. So after processing this, then here only one opening bracket will remain, and followed by that 3 closing bracket. Okay. Next yes on opening bracket. At opening bracket, what happens? S on opening bracket goes to S state itself. That's why here it is yes in the next step, and it performs it pushes that opening bracket onto the stack. That's why now it has become 2 opening parentheses. Next, S on closing parenthesis. Come to this. S on closing parenthesis goes to which state? S on closing parenthesis goes to yes state itself. That is why S on closing parenthesis goes to yes, that is yes, and because of that closing parenthesis, it pops the one opening parenthesis. So this will be removed from the stack. So you can see here only one will remain. Next comes to yes on closing parenthesis. S on closing parenthesis now will do what? Goes to S state itself. So it goes S on closing parenthesis goes to S state. That's okay. And after processing this, one character will remain, that is closing. And because of this, its effect, what you're going to do? We pop one opening parenthesis. So what is remaining here? Close. Now S on closing parenthesis goes to where? S on closing parenthesis is tries to need to pop one opening parenthesis from the stack, but our stack is empty, so that's why we can't proceed further. You can see here in this case we have reached to an accepting state, but input is not empty, but stack is empty. So if one of them fails, we cannot tell that particular input string as accepted or not. Okay, that is about the so that is why this particular input has been rejected by the PDA whatever we have drawn. Similarly, if you consider this example, you can look at the answers here. So even this also will not get accepted by the PDA. This is how you can solve the problems.